Good afternoon. We are now on the third part of our discussion on section 1.2, which is about Boolean algebra and logic gates. So we have here the basic logic gates, symbols for the different logic gates. For the AND gate, the symbol for the OR gate, 2-input AND gate, 2-input OR gate, the inverter, and the corresponding algebraic function of each of the logic gates. And on the rightmost column, we have the truth table. We have already discussed what a truth table is. We have the inputs x, y corresponding to the inputs of the logic gate. We list all the possible combinations of the inputs, and then on the other column is the output side. Here the output is f, and for each combination of input we have a corresponding output. This is a symbol for the inverter. We have already discussed this also. The inverter symbol is from the buffer symbol with a bubble at the end to indicate that this is a complement of the input, because we know that for the buffer it just transmits whatever is from the input. The logic value does not change for the buffer, but for the inverter it is being complemented. And we have here the NAND gate. The NAND gate is the complement of the AND gate. Therefore, it has a bubble at the end before the output signal. Notice that the output F is 1. The output F is 0 if both input are 1, which is the very opposite of the AND gate. That is the NAND gate. Then the NOR gate is the complement of the OR gate. We have another bubble here. We have the same symbol as the OR gate, but with a bubble at the output. Now this is the symbol for the exclusive OR, which has this Boolean function xy prime plus x prime y. As we discussed previously, this means that only one of the input must be high. One is high, the other is low. Same here, one is high and the other is low. That's for the exclusive OR function. We notice that the output is 1 whenever x is 0 and y is 1, or y is 0 and x is 1. Exclusive NOR. This is the complement of the exclusive OR. The symbol is the same but with a bubble at the output. Just the complement of the exclusive OR. And this is what we call the equivalence that we have discussed previously. Instead of the exclusive OR, we have the equivalence. This means that x and y are always equal. So the output is high if the inputs are both 0 or the inputs are both 1. If the inputs are, in other words, if the inputs are the same. Otherwise, f is 0. We also have here other examples of logic gates for multiple input gates. For letter A, we have a 3-input NOR gate. So how are we going to implement that? Just the usual OR operation for the inputs x plus y plus z, and then we complement the result. So x plus y plus z prime. For the 3-input NAND gate, it's the same as the AND gate with a complement. So xyz, the quantity xyz prime. Letter C, this is an example of a cascaded NAND gate. What is the Boolean function representation of this logic diagram? ABC, this is ANDed and then complemented. So ABC prime, then at the end it is being, we AND that with DE prime. So this is the function, equivalent function, Boolean function. ABC prime dot DE prime, and then complement, because this is a NAND gate. Then further simplification using De Morgan's theorem, we will arrive at the result ABC plus DE. You can check that yourself. Try to solve if the final answer is really ABC plus DE. Another example, we have the 3-input exclusive OR gate. For letter A, we implement this. So X exclusive or Y exclusive or Z, we implement this with two 2-input exclusive OR gates. So XY, we first perform exclusive OR of XY and then exclusive OR of XY and Z. You can check this yourself. Try to check this one if the result is going to be the same with the 3-input gate. For the 3-input gate, it is just using only one exclusive OR gate, but with 3 inputs instead of 2. They should have the same truth table, and it is 1 if there is an odd number of ones. Notice here, this combination of inputs has one value. This has 1, this has 2, which is even, so it's 0 at the output. Well, here we have 1, so it's 1 here. Here we have 2, so the output is 0 because the number of ones is 2, which is even. Same here, even, therefore output is 0. For the last one, we have 1, 1, 1, which is 3. There are 3 numbers of ones, which is odd. So we have 1 at the output, F. So when we use the exclusive OR, it means that the number of ones should be odd to make the output high or 1. Now let's go to positive and negative logic. Choosing the high level H to represent logic 1 defines a positive logic system. Choosing the low level L to represent logic 1 defines a negative logic system. Let's show through a figure. We say positive logic, it is the usual definition. So far we have used the positive logic from our previous examples. When the signal value is high, we say that it has a logic value of 1. However, for negative logic, we use the opposite. Logic value is 0 if the signal value is high. This is very common also in some implementations. Negative logic system is sometimes used, and it is more commonly known as an active high signal, for example. Active low signal. I have already seen so many examples where the signal used where the logic used for the enable signal is the negative logic system. And it's called active low. Let's go to the definition of the polarity indicator. The polarity indicator designates the presence of which along a terminal signifies that negative logic is assumed for the signal. Thus, the same physical gate can operate either as a positive logic gate or as a negative logic OR gate, positive logic AND gate, or as a negative logic OR gate. The truth table for this polarity indicator is shown here. It is high if both are high. It's just a positive logic AND gate, right? Low if not all inputs are high. Anyway, let's leave that. Let's just go here. The demonstration of the positive and negative logic. Positive logic AND gate. Yeah. Okay. It only associates the positive logic with the negative, so I just made a comparison. And the basis is the positive logic AND gate. With positive logic and with an AND gate, we just follow the truth table of the AND gate. So it is high if both of the inputs are high. And if we try to find the equivalent of this with the negative logic, what happens? With negative logic, the equivalent is it is high, but high is 0 in the negative logic, so we change all the zeros to ones and then all the ones to zeros from the true positive logic AND gate to get the equivalent negative logic. And then we try to find the implementation of this using the logic diagram. And this is the result. What does this mean, this triangular? Okay, this only signifies that we are using the negative logic. Instead of the positive logic. And why use the OR symbol? Okay. Using the OR symbol because if we look at the truth table, this is the OR operation, right? when there is one in either the input, in either or both of the input, then the output is 1. And that is the usual OR gate that we know, except that this is used for negative logic, so we add this triangular symbols to the signal lines of X, Y, and Z. In this book, we will not use negative logic gates and will assume that all gates operate with the positive logic assignment. So all throughout our discussion with Morris Mano's book, he will just use the positive logic. Integrated circuits. Integrated circuits, or ICs, these are fabricated on a die of a silicon semiconductor crystal called a chip, containing the electronic components for constructing digital gates. Excuse. We all know that ICs, there are two types, common types, the analog and the digital. So since we are talking about the digital side, we can construct digital ICs using the digital logic gates that we have discussed. The AND gates, the NOR gates, etc. But what's so nice and good about the digital IC design is most of the processes, the synthesis, the choosing of the gates, it will be done automatically, so we don't have to select every component. We just have to choose the standard cells or the libraries from those that are available, offered by the vendor, and the placement in the circuit. Sometimes it is automated. We just have to use HDL, or hardware description language, that we will be tackling in the next sections. We will design in digital using HDL, or hardware description language. It will make digital IC design much faster and automated using software tools that are available commercially. However, these tools are very expensive, that sometimes companies are the only ones that can afford it. Okay, let's move on to the levels of integration. The levels of integration in IC design, we have SSI, MSI, LSI, VLSI. Okay, less than 10, that's SSI. We are basing the level of integration to the number of logic gates. For MSI, we have 10 to 1000 gates. Examples of this are adders, multipliers, decoders. LSI, this is for large scale integration with thousands of gates. Examples are processors, microchips, programmable logic devices. While VLSI, it contains millions of gates, large memory arrays, complex. It contains millions of gates. Examples are large memory arrays and complex microcomputer chips. VLSI is a very common term in IC design. Let's go to digital logic families. This classifies ICs based on the circuit technology. The components employed in the construction of the basic circuit are usually used to name the technology. Examples of the digital logic families are the TTL, or transistor-transistor logic, ECL, or emitter-coupled logic, MOS, this is metal oxide semiconductor, CMOS, this is complementary metal oxide semiconductor. CMOS is the one that is commonly used in making ICs, whether digital or analog. TTL is an old digital logic family. ECL is used for high speed. MOS for MOSFETs for high density, CMOS for low power, and that's why it's dominant today, because of the requirement of smaller chips and low power. Most chips today are designed for low power applications. That's why CMOS is very dominant. TTL and ECL are now declining. Let's define some of the terminologies in digital circuits. Fan out, this specifies the number of standard loads that the output of a typical gate can drive without impairing its normal operation. A standard load is usually defined as the amount of current needed by an input of another similar gate in the same family. We know that we all know that we connect logic gates. One logic gate is connected to the next, and the output of a certain logic gate is connected to the next stage. Fan out, this defines the number of loads or logic gates that it can be connected to. This is usually defined as the amount of current needed by an input of another similar gate in the same family. So expressed sometimes in the amount of current that it can give to the next stage. Fan in, this is the number of inputs available in a gate. For example, if we have a logic gate can have 5 inputs, 2 inputs, depending on its capacity. Power dissipation is the power consumed by the gate that must be available from the power supply. Then propagation delay, the average transition delay time for a signal to propagate from the input to the output. This is also a very important parameter or characteristic of a logic gate. We want that the propagation delay should be small, very small. For example, if the input of an inverter switches from 0 to 1, the output will switch from 1 to 0. Yeah, because that is the function of the inverter. It inverts the input. But after a time determined by the propagation delay of the device. Yeah, it does not. We know that a actual physical hardware does not automatically change from 0 to 1. There is a certain delay, and that delay is what we call propagation delay of a logic gate. Noise margin is the maximum external noise voltage added to an input signal that does not cause an undesirable change in the circuit output. This is the amount of noise that is tolerable by the logic circuit. that will not affect its operation. And then beyond that, if the noise is greater than the noise margin, then we have a problem because the circuit might not function well because of the noise, too much noise. Computer-aided design of VLSI circuits, or CAD. Computer-aided design is abbreviated as CAD. Then electronic design automation, that's EDA. There are a variety of options available for creating the physical realization of a digital circuit in silicon. The designer can choose between an application-specific integrated circuit, excuse, a field programmable gate array or FPGA, a programmable logic device or PLD, and a full custom IC. So there are different ways that we can create a digital circuit. Application specific IC, full custom IC, FPGA, and PLD. I think I'm more common with the ASIC, FPGA, and the full custom IC. This is search for Synopsys and Cadence EDA tools in the internet and watch YouTube videos about the tools. These IC design companies provide IC design EDA tools for analog, digital, mixed signal, and RF ICs. Yes, in the market today, these are the biggest companies in IC design. IC design software tools. They sell their own company software tools, Synopsys and Cadence. I have tried both of them, and they say that for analog, Cadence is much better in implementing analog IC designs. That's what they say. While Synopsys is more on the digital. You may just experience it yourself to research which of these two are suitable for a particular application or IC that you want to design. This is where we start discussing about HDL, though I have already mentioned it. HDL is a hardware description language used in digital IC design. From the word itself, hardware description, so we describe the hardware. We are trying to describe the actual circuit using a language. This HDL, a hardware description language. And the two most popular HDL are Verilog and VHDL. You can use either two. Some companies use VHDL, some use Verilog. Verilog, they compared Verilog to C language because it is much easier and less formal in declaring the syntax is similar to C language. It is easier, lighter. Anyway, it depends on your preference. But still other companies use VHDL. And others use Verilog. Two HDLs, Verilog and VHDL, have been approved as standards by the Institute of Electronics and Electrical Engineers, so they're already IEEE standards and are in use by design teams worldwide. But here we will use Verilog all throughout, so if you're interested with VHDL, you can do a research for yourself also. It's good to know both. About FPGA, I want to say something about FPGA. There are available FPGAs in the market, and there are also FPGA training kits or development boards that you can buy. This is good for practicing digital IC design, and most, I think, FPGAs are capable. FPGAs use Verilog, either Verilog or VHDL. ASIC. In designing ASIC, you really have ASIC or full custom. You really have to use the softwares, EDA software tools from Cadence or Synopsys, but they are somewhat expensive. So FPGA is a good starting point. And also FPGA is widely used in prototyping ASIC, so you can start with FPGA before you design in ASIC. Because in FPGA, the design, IC design can be changed. You can change your design. You program the FPGA, you simulate, you load your program to the FPGA, simulate, and then you can even later change your program. So there's no waste. It's like a microcontroller, but in microcontroller, just like Arduinos, you can't change. You can change what's inside the chip, the microcontroller chip. You are thinking of the application directly. The inputs and the outputs, adding sensors. But for the FPGA, it is more closely related to IC design instead of focusing on the application. You focus on the internal design of an IC. Which is a digital IC. Research activity, just do it for the students. My students, just do it. Just perform the indicated research activity. So that ends our discussion for section 1.2. Our next topic is 1.3, which is about gate level minimization. Thank you for watching, and please subscribe.